This is a demonstration on how to fit a quadratic growth curve model using M+. And the data that we're using here is child internalizing problems from age 10 to age 16. So here we have our variables, 7 variables, age 10 to 16, all summary scores of an internalizing scale that they took every year. Now we have our model. I just, for convenience sake, named the intercept I and the linear slope L. There's our bar. And then here we have what you'd expect, our variables listed. And we have the at 0, at 1, at 2, at 3, on up to at 6. We also have our plot command down here so we can take a look at what this trend over time looks like. Now I don't have my quadratic in here because we first want to just take a look at what this model fits like and what the parameters are when we assume linear growth. So let's go ahead and fit that model and look down, and we see our RMSEA here. The estimate is really bad. It's above 0.06, above 0.08, which may indicate marginal fit, but we're at 0.11. That's pretty high, indicating that our hypothesized model of a straight line linearity doesn't seem to work here. Our CFI also is poor. We'd like to see that above 0.95, and that's at 0.894. So these fit statistics indicate that our hypothesized model linearity doesn't quite do the trick here, doesn't quite explain the data. Here's our model results, our intercept and slope, again all at 1 and then 0 through 6. Our correlation between the linear slope and the intercept is significant. And here are the means. The mean of the intercept is 0.405, and the mean of the linear slope is negative 0.004. Quite low, and in fact it's not significant. So from this we would conclude that there is no change over time. If we were to stop here with this model, we would conclude no change over time. You see variances here, and the variance in the intercept is significant, so we can predict that, but also the variance in the slope is significant. So although there's no overall average change in child internalizing problems from age 10 to 16, it does appear that there's significant variance in that. But again, this doesn't fit the data very well. So let's go ahead and examine a model when we add a quadratic term. And again, M+ is probably the easiest program to do this in. All we do is we simply add the name of a variable here, Q, and that's it. We now have a quadratic growth curve model. Again, everything before that bar, it just knows that the first term, that I, is the intercept. It knows that the second term is the linear slope, and then now it knows that the Q is the quadratic slope. So we haven't done anything to this model other than add that Q, but now this is a quadratic growth model. So we'll save that, and we'll fit that model, and we can go down and look at our fit statistics again, and you can see that we have a much improved model fit. The estimate here is 0.079, so that's below the 0.08, so it's acceptable model fit from the RMSEA standards, but the CFI is above 0.95, and so that's in the good range for that. So our model fit has really improved quite a bit, and we might even say that this is a pretty acceptable model, that this is a model that we could accept given these criteria. Now as we go down, we see our correlations, or I say covariances, it's reported here between the linear slope and the intercept, the quadratic slope and the intercept and the linear slope. And here we have our means. It actually now, our linear mean is significant, whereas it wasn't before. Sometimes when you add the quadratic slope, there's no real difference in the linear. It might change a little bit. Of course, the intercept won't really change, but the linear slope won't change all that much at all when you add the quadratic, because the quadratic really doesn't have much of an effect. But here we do see that the quadratic is significant, that there is a significant curve in this. trend over time. And you can also see here our variances. There's significant variance in the intercept, significant variance in the linear slope, as well as significant variance in the quadratic slope. Now, it's pretty low. You can see these are zeros. If we were able to pull this out a few decimals, you'd be able to see that. And in fact, in Stata, you would be able to see that. If you watch the Stata version, you'd see decimal places all the way out. And so this is in fact significant. So we might even be able to predict that quadratic slope as well. So dramatic differences when we're looking at the quadratic slope instead of just the linear. That fits the data much, much better, and also you get a significant linear slope and you have significant variance in the linear quadratic slope. So this is a much different model, fits the data much better. Now let's go ahead and look at our graphs of this. So we're going to click on that. Again, we asked for those plots above. We're going to look at the estimated means, and there's our bend. So from age 10 to 16, we see that internalizing problems seem to decrease during that time. To the point of, this is 10, 11, 12, 13. So age 13, it seems that internalizing problems are pretty low, but then as you get into 14, 15, 16 range, something's happening where kids seem to be, on average, increasing in their internalizing problems. And again, we can predict this slope, we can predict the intercept to see how kids might vary from this. It might be that some kids go down and they just stay down. It might be that some kids are a little more flat in their internalizing problems. Maybe flat and high, maybe other kids are flatter and lower, but we can use some other variables to predict that. So this is how to fit that quadratic growth in M+. Again, probably the easiest way I've ever seen of how to do that. And let's just for fun fit a cubic one. It may not be that it's just this pretty regular change. It might be that there's other change going on there. So just for fun, I haven't actually done this before, so we'll see how it works. And to fit the cubic model, well, all I do is I add the c in there. Because I have more than 4 time points, I can fit that cubic model. Now, sometimes these cause a lot of stress in the data, not in the data, but in fitting the model. That's pretty complex, so let's see what we get here. So that fit, and no convergence, serious problems and iterations, check your data, starting values, and model. Well, you can here see that are cubic, but it's not going to fit. And there's probably a lot behind why it's not fitting. That's a pretty intense model, fitting the cubic. And so I'm not going to dig in and find out exactly why that quadratic fit the data pretty well, so we're just going to go with that.